Hi, welcome. What I'm going to be covering in this video is a look at the mathematical analysis of free energy and thermodynamic favorability. So the formula that we're going to be focusing on is delta G naught. We're going to be looking at that balance between delta G naught minus T delta S naught. Now, an important consideration here is, for one, we're going to assume the temperature is 298 Kelvin. All right. It is typically assumed that delta H and delta S are independent of temperature. So I could change that temperature these values would remain the same. Now, clearly, delta G is dependent on temperature. Okay, so the question may not state that, assume that the enthalpy and entropy are temperature independent, but that's being assumed in the context of the question. Now, an approach that I will often take is to list your givens, write your equation, list your givens, check your units, write your equation, substitute, solve. All right. On an AP test or on your college test, IB test, you may not have time for that. So our givens are labeled pretty well. So sometimes I'll label my givens within the context of the questions. But for sure, we've got to check those units. Notice that we've got kilojoules for delta H and joules for delta S. You're going to have to do some level of converting so that your units are the same. We have our equation, so now I'm going to substitute and solve. Delta G naught is going to be plus 119.2 minus that 298 that I added. It should have been in the question, but many tests will say at the beginning that you need to make the assumption that it's at 25 degrees Celsius or 298 unless you're told otherwise. So that's 298 Kelvin. And now I have to convert one or the other for no reason at all. I'm going to convert my delta S to kilojoules. All right. Now, I want you to notice that my delta H in this case is unfavorable and my delta S is positive or favorable. I think it's always good to do an analysis of this. So this is what we would call an entropy-driven process. If it's entropy-driven, we would want to maximize temperature. So increases in temperature would make it more favorable. Just kind of adding a little bit of that qualitative I've done in a previous video to that. Now, if you do this mathematics, you're going to get about 43.0-ish. I didn't write that decimal down, and I just noticed I should round to my furthest decimal to the left or my least certain decimal to my left. So I'm going to assume that's a 0, and then we would have kilojoules per mole of reaction for this process. Okay, so now let's look at another application of this equation. It's not uncommon to actually have to calculate the temperature at which a process becomes favorable. So for this one, I have the synthesis of ammonia. I have a favorable enthalpy. I have an unfavorable entropy. Hopefully you could predict that because I have all gases, but I go from 4 moles of a gas to 2 moles of a gas. That's less free, less dispersed, fewer microstates. So that's a negative delta S. All right, so now to do this, what we find, let me sketch this for you. So this would be my delta G naught. That's my temperature on the x-axis. If I have an unfavorable delta S, that means it's enthalpy driven. as I increase temperature, it's going to become less and less favorable because that increase in temperature is going to start maximizing or amplifying that unfavorable entropy. Okay, now the crossover point, that's what the question's asking us. At what temperature does it become spontaneous? We've already answered the question that it will be below. It is an enthalpy-driven equation or reaction. Okay, so now we're going to say 0 is equal. I'm going to put a 0 in for my delta G. Check those units. Make sure you have both kilojoules or both joules. It doesn't matter which one. I don't know my temperature, and I've got a minus 0.19875. Okay, and if you solve this for your temperature, you should get 464.0 Kelvin, right? If you rearrange that for temperature, temperature is going to equal delta H naught over delta S naught. Just make sure they're the same units, both joules, both kilojoules. So this is that crossover temperature. This would be the temperature that's represented right there when delta G naught's 0. And it's going to become more and more thermodynamically favorable below this temperature. So those are two key applications of that major equation. Sometimes I just call it the GHS equation as I'm referring to it. So the GHS equation gives us that balance of enthalpy and entropy to determine whether a reaction or process is thermodynamically favorable. Okay, thanks for your time. For my kiddos, until I see you in class, this is signing off.